Welcome to the session. Today we are going to discuss some of the theorems in planar graphs, dual of a graph and graph coloring. So here, regarding planar graph, Euler's formula. In the last session, we directly took the Euler formula as this and we solved some of the problems. Now we are going to derive the Euler's formula. So here the theorem statement is a connected planar graph G with n vertices and m edges has exactly m minus n is equals to 2 regions in all its diagrams. So number of regions is nothing but m minus n plus 2. Sorry, this is plus m minus n plus 2, or that is can be written as n minus m plus r is equals to 2. So this is the theorem statement. Now we are going to prove this. So number of regions are r is equals to m minus n plus 2. This we have to prove. So if number of edges, if we are going to take it as E, and the number of vertices we are going to take it as V plus 2, this also we are going to consider. But we are considering number of edges is m and the number of vertices are m. So we are going to take, this is the Euler's formula. Now we are going to derive this formula. So to derive this formula, we are going to use a mathematical induction on m. M is nothing but the number of edges. So here we are going to take the induction step, that is if m is equals to 0. This is the induction step. Whenever m is equals to 0 means the number of edges are zeros. So there is no edge. So now the number of vertices must be equal to 1. Suppose if the number of vertices are more than 1, greater than 1, let us say 3, and then G will have at least 2 vertices. Let us, if I am going to consider, then at least 2 vertices or 3 vertices or whatever it is. So it is given the graph is a connected one. The graph is a connected graph. Okay. So now we are going to connect them. If we are going to connect this, then automatically edges will be more than 0. So we are going to take number of vertices must be 1. Whenever number of vertices is 1, and m is equals to 0, then it provides only one reason. That means we are going to substitute r is equals to number of edges 0, number of vertices was minus 1 plus 2, so it is equals to 1. So which is nothing but whatever we are going to consider other than the vertex, that is the only reason. Other than the vertex, the entire thing we are considering it as the reason, so that the reason is we are taking it as r infinity. That means we are going to say that the induction step is true for m is equals to 0. Now let us assume that it is true for m is equals to k. This is assumption. Let us we are going to assume that m is equals to k. The theorem is true. Now we are going to prove that it is true for m is equals to k plus 1. Now we are going to prove, if we are going to prove this, then by induction method, by mathematical induction, we can say that for all number of edges, the theorem is true. So this is the assumption. That means whenever gk, which is having k edges, that means m is equals to k edges. So the corresponding graph we are going to take it as gk. Now we are going to consider number of edges are k plus 1. Let us we are taking it as the graph, the corresponding graph, we are going to take it as gk plus 1. a graph is gk plus 1, which is having k plus 1 edges. Then automatically it is having two different cases. One is if it contains cycles, that means the graph contains cycles, and another one is it does not contain cycles. It does not contain cycles. It does not contain cycles. So these are the two possible cases, any graph if you are going to consider. So now gk plus 1 is the graph which are having k plus 1 edges. Now let us assume that it does not contain any cycles. If the graph does not contain any cycles, then automatically it is a circuitless. It is a circuitless. Then we can say that it forms a tree. It forms a tree. Let us, I am going to say that a graph gk plus 1 is, we are going to take g of k plus 1 is like this. So which is circuitless or cycleless. So we can say that this is a tree, and how many reasons it is going to be providing? The reasons is other than the tree, other than the graph itself, So the number of reasons are 1 we are going to get. Now we are going to verify whether from the formula we are going to get number of reasons are 1 or not. So here r is equals to m is nothing but number of edges. So here we are going to consider k plus 1 edges. So I am going to take m is nothing but k plus 1. And how many number of vertices it is having? Any tree, if it is having n vertices, then it is corresponding n minus edges this is having. Any tree, number of vertices minus 1, those many edges will be there. There are many edges will be there. So here k plus 1 edges. So number of vertices are k plus 2. Number of vertices are k plus 2 we are going to take. Then if I am going to simplify this, so finally we are going to get number of reasons are 1. Number of reason is 1. So this gives a reason which is providing other than the graph. So the theorem is true for a graph which is having k plus 1 vertices, k plus 1 edges, and it is free from the cycles. Now we are going to concentrate on this. Suppose g of k plus 1 will have cycles. So whenever cycle will be there, how we are going to get a reason? So for that, the reason degree is, minimum degree is 3. Minimum degree is 3 we are going to. Or is, let us say, it will have a cycles and it does not. So the cycles are going to be formed with the 3 edges or with the 4 edges or with the 5 edges like that. So there are some reasons will be there in this graph. So let us consider R be the number of reasons. So it will give, we will have a cycle, then automatically it will give then reasons, it will give R reasons. This is assumption. Let us assume that it is having R reasons. So let us assume that it has R reasons. So now, if it is having R reasons, then suppose, that means let us consider, I am taking one example is like this. So here it is having cycles, let us say. So now, just I am going to consider a graph is like this. This is having some reasons. So one edge will be there. One edge. If I am going to remove the edge, then automatically the number of reasons are also going to be reduced by 1. So here, let us assume that it is having k. Suppose if I am going to remove one reason, if I am removing one edge, let E be the edge. If we remove, then number of reasons are r minus 1. Number of reasons are r minus 1. So let us, it is having, we are assuming that number of edges after removal e, then we are going to say that if I am going to remove one edge, automatically how many edges it is having? It is having k plus 1 edges. So if I am going to remove one edge, then automatically how many edges it is having? K edges. It is having k edges. Now, what is the formula is, just I am going to take r is equals to, just we have to consider r is equals to m minus n plus 2. So it is a m minus n plus 2. So here what is m is k, n is how many number of vertices it is having, let us say n, and then we don't know that, then it is 2, then I am going to take it as a k plus 1, then minus n, and next here this is how many reasons it will be, reasons also it is going to be reduced by 1. So I am going to get like this, so r is minus 1 is this, and this I am going to write it as plus 1, so r is equals to k plus 1, then minus n, and this plus 2. So I am going to get equation. So here what I am saying that this equation, that means r is equals to m minus n plus 2, which is the Euler's theorem, number of reasons, and it is going to be satisfied a graph which is having k plus 1 edges, So the theorem is true, for n is equals to k plus, for m is equals to k plus 1 edges, So here the induction step is just we are going to consider, we are going to take whenever m is equals to 0, then we are going to verify whether the theorem statement is true. Then we are going to assume that m is equals to k, the theorem is true. That means number of edges are k, then the theorem is true. And k plus 1 edges where we verified. First one is it contains cycles, it does not contain a cycle. So if it does not contain a cycle, then it will form a tree. Then whenever it form a tree, then the number of reasons are 1, and that is verified by using this principle. And whenever it is having a cycles, then if it will provide r reasons, let us assume that it is providing r reasons. Now if I am going to remove one edge, number of reasons are r minus 1. Then number of edges are k only. Then whenever number of edges are k, then automatically the theorem is true for m is equals to k. So we are going to write it as the Euler's theorem is true for m is equals to k. So I am going to write, this is, I am going to use the assumption step, hypothesis. That means we are going to assume the theorem is true for m is equals to k. So for that I am going to take this. And next m is equals to r is equals to r, number of reasons also reduced by 1. So this is r minus 1 we took, and k minus n plus 2. Then r is equals to k plus 1 and minus n plus 2, which is nothing but the given Euler's formula is satisfied by m is equals to k plus 1 edges. So we can say that the theorem is true for m is equal to k plus 1 edges. Subsequently, by mathematical induction, we can say that this is true for all number of edges. So this is the way that we are going to prove the Euler's formula for planar graphs. Next, one corollary will be there. So here, if G is a connected simple planar graph with n vertices, n we are going to consider greater than or equal to 3, and m is nothing but number of edges are greater than 2, and r reasons, then we have to prove this, and we have to prove this. So here it is given, it is a simple planar graph. It is a simple planar graph means it is given already simple planar graph. Planar graph. So it does not consist. It does not consist self loops and multiple edges. And multiple edges. That means no loops and multiple edges, it is not going to be there. So now the reason, say it is given a planar graph, so it has some reasons. So the reason is bounded by 3 at 3 edges or more than 3 edges. 3 edges are more than 3 edges. So here let the planar graph will give number of reasons are R. R be the reasons of the graph G. Let us say G be the planar, simple connected planar graph. And now each reason, what is the sum of the degrees of reasons, which is equals to even number, that is nothing but 2 into number of edges. So here, how many reasons are there? There are R reasons are there. Each and every reason must be bounded at least 3 edges. So degree, let us say the number of reasons are, we are taking it as R1, R2 and so on RR. So what is the degree of R1? Degree of R1 is greater than or equal to 3. And similarly, degree of R2 is greater than or equal to 3. And so on. Degree of RR is greater than or equal to 3. Then I am going to add all the things. So degree of R1 plus a degree of R2 plus and so on degree of RR is greater than or equal to 3R. So this is nothing but the sum of the degrees. So here degree of Ri, I is equals to 1 to R, which is equals to 3R. So what I am going to write, this is a 3R greater than or equals to, not equal to, greater than or equal to. So which I am going to write it as 2M is greater than or equal to 3R. 2M is same, greater than or equals to 3R. By using this is nothing but 2 into number of edges. So 2M. So M is nothing but greater than or equals to 3 by 2 into R. 3 by 2 into R. That is the first one. And the second one, if I am going to calculate, that means the first one will give the relationship between M and R. Now the second one is giving the relationship between M and N. That means number of vertices and number of edges. So M is greater than or equals to 3R means 2M is greater than or equals to 3R. So which is greater than or equals to? What is the Euler's theorem is? It is a simple planar graph. It satisfies Euler's theorem. So it is nothing but number of reasons are M minus N plus 2. M minus N. So it is M minus N plus 2. So which is nothing but 3M minus 3N and plus 6. Then this will become, so it is 3N minus 6 is greater than or equals to 3M minus 2M. So it is 3N minus 6 is greater than or equals to M. Or we can say that M is greater than or equals to 3N minus 6. So this is the relationship between number of vertices and number of edges. Whereas the first one is, will give the relationship between number of edges and number of reasons. So this is the corollary one states like this. That means the relationship between number of vertices and number of edges or number of edges and regions if for a simple planar graph. Now the second corollary. So by using this, so here prove that the Kuratowski's first graph is non-planar. So Kuratowski's first graph is nothing but a complete graph with 5 vertices. Let us taking the complete graph with 5 vertices is like this. So I am going to consider a complete graph with 5 vertices. So like this. So it is connected to all the vertices. Now next vertex is also connected to all the remaining vertices, and here it is connected, and this is connected, and this is connected. It is a complete graph with 5 vertices. So this is so now here we are getting like this. Now here how many vertices it is having? N is equals to 5. How many edges it is having? M is equals to, see here 1, 2, 3, 4. Next 5, 6, 7, 8, 9, 10. So it is number of edges are 10. Now suppose if I am going to assume that this is a planar graph, then it satisfies the relationship between number of vertices and this number of edges. So here I am going to take the number of vertices, number of edges relationship is this, and if it is a planar graph, so m is less than or equals to 3n minus 6. So I am going to verify m is less than or equals to 3n minus 6. If it is there, then it is a planar graph, otherwise it is not. So m is 10 is less than or equal to 3 into 5 minus 6. So 10 is less than or equal to 15 minus 6, which is 9. So 10 is less than or equal to 9, which is meaningless, which is not true. Hence, we are taking, let us assume that, let G or K5 is a planar graph. K5 be a planar graph. So this is the assumption. If it is a planar graph, this should satisfy. This is not satisfied, then our assumption K5 is not a planar graph. So what we are saying? K5 is not a planar graph. K5 is not planar graph. This is this. And the second one, show that Kuratowski's second graph. This is nothing but a complete bipartite graph. Let us, we are considering a complete bipartite graph. Is this? And now, so it is connected to all the other vertices which it is in the other set. Let us say this is one partitioning and this is another partitioning. So in this, suppose if you are going to take it as K33 is a planar graph. So if it is a planar graph, how many vertices it is having? Number of vertices are 6 and the number of edges are 9. So this is 3, this is 3, this is 3. So number of vertices are 6, number of edges are 9. Now here, it is going to be, let us assume that I am taking this is a planar graph, then it has regions, and the regions are bounded by how many number of edges? This is just we are going to consider one region I am going to get. This is like this I am getting. So one cycle, I am getting one cycle. So it is formed by, which is formed with 1, 2, 3, 4. So the region is formed by 4 edges. Minimum is 4, and if it is more than also 4 is possible. Now what we are going to take, the K33 has no triangles. So here region is bounded by only 4 edges. Now let us say I am going to have, it is having R edges, it is having R regions, then what is the degree of each region? What is the degree of each region? So R regions, let us say R1 and next R2 and so on RR. Be the regions. Be the regions. Now, what is the degree of R1 is? Degree of R1 is greater than or equals to 4R. Degree of R1 is greater than or equals to 4. Degree of R2 is greater than or equals to 4. And so on. Degree of RR is greater than or equals to 4. So if I am going to add all the things, then degree of VR1 plus degree of R2 plus and so on, degree of RR is greater than or equals to 4R. This is nothing but the sum of the degrees of regions, so which is nothing but 2 into number of edges, which is greater than or equals to 4R. So M is greater than or equals to 2R. M is greater than or equals to 2R I am getting. So whenever M is greater than or equals to 2R, then it is a planar graph. So call this as 1. Now in this, I am going to substitute what is R value. So M is greater than or equals to 2 into R is equals to. So R is, what is the Euler's formula? R is equals to M minus N plus 2. M minus N plus 2. So we are going to substitute that. M minus N plus 2. So I am going to get M is greater than or equals to 2M minus N plus 2. Which is nothing but just taking to that side, or else this is N minus 2, which is greater than or equals to M, which is greater than or equals to 4. Sorry, this is 4. This is also 4 I am reading. So this is 2N. Sorry, this is 2N. 2N minus 4. So what is that? This is 2N minus 4 is taking to that side and greater than or equals to 2M minus M, which is M. So M is less than or equal to 2N minus 4. This is one inequality. This is one inequality if it is a planar graph. Now, that inequality is going to be satisfied or not, we have to verify by substituting whatever the number of vertices and number of edges we have. So N is equals to 6 and M is equals to 9. So just to substitute here. So this is M is equals to 9 is less than or equals to 2 into 6 minus 4. So which is 9 is less than or equal to 8. Which is not true. Which is not true. So this is not true. So we can say that our assumption that it is a planar graph is wrong. So K33 is not a planar graph. K33 is not a planar graph. So we are assuming that K33 is a planar graph. Then this inequality should be satisfied. Let us say this is equation 2. And then the equation 2 is going to, inequality should be satisfied. So whatever the Krutowski's second graph is having, how many number of vertices, how many number of edges, that if you are going to substitute here, and this inequality is satisfied. So here this inequality is not satisfied. So our assumption that K33 is a planar graph is wrong. So K33 is not a planar graph. Now, let us go for the other example. So here, show that every connected simple planar graph with less than 12 vertices must have a vertex degree less than or equal to 4. Must have a vertex degree less than or equal to 4. Now here, I am going to assume that. So here, suppose, this is assumption, suppose every vertex G has a degree. Every vertex G has a degree greater than 4. See here we are going to prove this less than or equal to 4, then which is having less than 12 vertices. Then I am taking every vertex degree is greater than 4. Let us assume that the graph is having v1, v2 and so on, vn vertices, then degree of v1 is greater than or equal to 5, because I am taking that each and every vertex degree is greater than 4. So next, degree of v2 is greater than or equal to 5, and so on. Degree of vn is greater than or equal to 5. So it is nothing but degree of v1 plus degree of v2 plus and so on degree of vn is greater than or equals to 5n. Is greater than or equals to 5n. So this is by handshaking property. This is a sum of the degrees of all vertices. So degree of vi is greater than or equals to 5n. I is equals to 1 to n. Now this is 2 into number of edges. 2 into number of edges. So let us say 2 into number of edges. If it is having m edges, then it is 5n. So I am going to get m is greater than or equals to 5 by 2n. Call this as equation 1. Now, so I am getting a relationship between m and n. So what is the first corollary? This is m is less than or equals to 3n minus 6. So we are going to consider that. So what is that? M is by corollary less than or equal to 3n minus 6. We are going to consider the relationship between m and n. We are going to take this. Now here, this is going to be substituted. Now we are going to verify. This is what is a 3n minus 6. 3n minus 6, which is greater than or equal to m. What is m is? By equation 1, which is greater than or equals to 5 by 2n. So which is 2 into 3n minus 6 is greater than or equals to 5n. Then it is a 6n minus 12 is greater than or equals to 5n. So now it is n is greater than or equal to 12. So if I am assuming that a graph which is having each and every vertex degree is greater than 4, I am getting the number of vertices are equal to 12 or more than 12. So from this we can say that the complement of this, that means we are going to consider a graph which is having number of vertices are less than 12. Number of vertices are less than 12. So from this, if it is greater, each and every vertex degree is greater than 4, I am going to get the number of vertices are greater than or equal to 12. Greater than or equals to 12. So if number of vertices are less than 12, then each and every vertex degree is G has a each and every vertex degree is less than or equal to 4. Less than or equal to 4. This is the that's what they have to ask. So we are going to prove in this manner. Now, these are the some of the problems which are related for the planar graphs. Which are related for the planar graphs. Now we are concentrated only on the theorem proofs and some of the examples which are related to that. With this, I am concluding. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.